Hello again, friends. In this video we're going to be talking about our comparison test. So like I said in the last couple of videos, the comparison test really relies on having a firm understanding of some of our more popular, as I'm calling them, known series. So these kind of include our geometric series, our harmonic series, our P series, some of these more easy forms to work with. So our comparison test states that if our known series is convergent, we know that then our given series will be convergent if our known series is greater than our given. That's the comparison we're trying to test, whether or not it's greater than or less than. Similarly, if our known series is divergent, we know our given series is divergent when our known is less than or equal to our given. So in this video we're going to be working with our series I have written down here below. And the first question we have to ask ourselves is, okay, what does this series look like? If we were to, if he were to change just in the smallest way, what could he be? So in this series we have something, when we think about it, it kind of looks similar to the work we've done in the past with our geometric series, right? And I know that our geometric series are series of the form, we have n equals 1, a to r, 1 minus n minus 1. So this is our geometric series. And so how does this compare? How would this look like a geometric series? What we see is every geometric series, right, has this common ratio r. And this series we see kind of has that going on. We have our 3 to the n and 2 to the n. Right, this could kind of be our common ratio. The only thing that stops this from being a geometric series is that each term has this 4 added to it, and it's not being affected by a common ratio. It's just adding a 4 to each term. There's no multiplication of a common ratio to our 4. It's just added on. So if we were to rewrite this guy, more or less, as a geometric series, if he were a geometric series, he would kind of look like we'd have our 3n over our 2n. And so now we have to determine whether this series that we've kind of made up is convergent or divergent. This is our known series. So in order to determine whether a geometric series is convergent or divergent, we have to find our common ratio, right? So in this one, our common ratio is pretty easy. He's going to be 3 over 2, right? Based off what we know about our geometric series, we have to identify our a's and our r's, and our r determines whether or not we have convergence or divergent. And since our r in this one, by our geometric series, is greater than 1, this means this series is divergent. So now we have to establish our comparison. We have to determine how does that affect our given series. So our comparison for this guy, we're going to be comparing 4 plus 3n, and we're going to be comparing 2n over 2n. We're going to be comparing that with our 3n over 2 from our new geometric series that we made for ourselves. So when you look at these two guys, we're going to be looking at some nth term, right? Some term n into infinity. So we don't want to just use when n equals 1 or something, because that can affect how our series works. So sometimes it might be less at the beginning, but eventually as we go into infinity, our series converges to some number greater than what our known series is. So we have to think about some nth term as we go into infinity and compare. So our denominators for these two guys are the same. So what we're really looking at is our numerators. So we have 3 to the n, and here we have 3 to the n. The only difference is we have our plus 4, right? So since we're adding 4 on, we know that this term is going to be greater than our given series, is going to be greater than our known series, right? So our known is less than our given, so that satisfies this right here. Our known is less than our given. We know our known series is divergent, so therefore we can conclude our given series will also be divergent. So this guy right here diverges.